Good morning. It's my pleasure to be here sharing my work on Wi-Fi-based multitask sensing. Briefly speaking, this talk is about how to recognize gestures, locations, and users by using Wi-Fi signals. My talk will be in 4 parts. At the very beginning, I will introduce the basic principle, pros and cons of Wi-Fi-based sensing technology, and the motivation of the multitask sensing work. Later, some related researches will be reviewed. Subsequently, the methodology will be discussed. In the final part, the experimental results will be illustrated. So first, we talk about the background. The rationale behind Wi-Fi-based sensing is that human behaviors can bring about singular fluctuations that can be extracted from the physical layer feature of Wi-Fi, namely Channel State Information (CSI). As illustrated in Figure 1, the Wi-Fi signal may interact with humans in propagation. Hence, the variation of CSI will contain the information of human behaviors. On the right side, there is a picture of the amplitude value of a CSI sample. More details about it will be discussed later. Now, I will talk about the pros and cons of Wi-Fi-based sensing. In fact, there are methods that enable human sensing to rely on cameras, wearable devices, radars. However, these methods may incur extra equipment costs or raise privacy issues. In recent years, Wi-Fi-based sensing methods have received immense attention. This technique has the following advantages. First, it enables non-line-of-sight sensing. For instance, it can perform the through-wall human pulse estimation. It is non-intrusive, off-device, and widely available. In contrast, there are some flaws of this technique. As depicted in Figure 4, the CSI sample is a 4-dimensional complex matrix, and the dimensions are the number of receiving antennas and transmitting antennas, the number of subcarriers, and the number of step shoots. There are different devices and settings for CSI data collection. Due to the lack of standard, different public datasets have different data formats that highly affected the objective evaluation of Wi-Fi-based sensing methods. And there is no semantic meaning in a CSI sample. For instance, we can't figure out what the human gesture type is by looking at the CSI sample directly. In addition, the CSI sample has no spatial information compared to images, which means that we can't estimate the position of a specific static object by adopting the CSI sample, while it can be done by using camera-based sensing technique. As mentioned before and shown in Figure 5, Wi-Fi signals are absorbed, diffracted, reflected, or scattered by other objects during propagation, leading to the high coupling between CSI and other factors besides human behaviors. The residual information of the other factors can be regarded in opposite perspectives. On one hand, the residual information is noise for the human behavior's recognition, so there is a lot of researches on the cross-domain or the robust Wi-Fi-based sensing methods. On the other hand, in our view, the residual information can be useful for accomplishing multiple sensing tasks simultaneously. Okay, let's move to the related works. Recently, Wi-Fi-based sensing has aroused immense attention. I classified these methods into 3 categories. The first category is the model-based approaches that based on the physical models or principles, such as the statistical theory of the electromagnetic waves, or try to extract it physical features, such as angle of arrival, time of flight, or Doppler frequency shift. The next is data-driven approaches. Some researchers adopt statistical learning or deep learning methods to extract features and perform the recognition task. These two types of approaches have different advantages. Hence, the other type of approaches is the combination of model-based and data-driven approaches. Now, the multitask learning is a subfield of machine learning that is dedicated to constructing one model to perform multiple tasks simultaneously. There are two challenges. One is the task imbalance issue, and the other is the task discrepancy issue. The task imbalance issue is that the multitask learning model is dominated by a particular task, leading to unacceptable performances of other tasks. And the task discrepancy issue is that different tasks need their task-specific features. The lack of task-specific feature may degrade the performance of the multitask learning model. Even worse, the task-specific information of different tasks may contrast to each other, which means that one's useful information may others noise. And these challenges also exist in the Wi-Fi-based multitask sensing, and we try to solve them in YMUs. The knowledge destination proposed by Hinton is dedicated to transforming the learned knowledge in an ensemble of models into a single model, and is adopted in model compression, transfer learning, domain adaptation, and multimodal learning, etc. In this work, we adopted the knowledge destination technique to address the task imbalance issue. Okay, let's move to the crucial part, the methodology of this work. The problem addressed in this paper is the Wi-Fi-based multitask sensing under the aforementioned challenges, task imbalance and task discrepancy. As illustrated in Figure 6 and 7, the datasets contain different types of gestures collected in different indoor locations, and we try to construct a model to recognize the gesture type, the location, and the user at the same time by using the CSI sample. The proposed model consists of different basic modules. The shadow encoder is for extracting the features directly from the input CSI sample. And then, by using the low-level features which extracted by the shadow encoder, the deep encoder is adopted to extract high-level features. In addition, to deal with the task discrepancy issue, a task-specific residual adapter is adopted to gain the task-specific feature from the low-level features. For each classification task, a classifier is adopted to output the logits. Then, by using a softmax function on the predictive logits, the probability over categories is produced. Now, this is the shadow encoder, which is contain a grouping convolutional layer and a max pooling layer. And this module, the deep encoder, is constructed based on the structure of ResNet. And the task-specific residual adapter contains only one convolutional layer. Finally, the classifier contains a convolutional layer and a fully connected layer. Okay, as we can see, this is the YMUs model. And the two sides are the trained single task models. When training the YMUs in such two tasks, user identification and gesture recognition, we first train two single task models corresponding to these target tasks. To solve the task imbalance issue, the NERD common features, namely the output of the deep encoder of Y-mills and the logits, should get close to the corresponding features and the logits in the single task models. The loss functions are defined by using cross entropy and Euclidean distance. Furthermore, to address the task discrepancy issue, two ratio adapters are adopted in Y-mills. At last, the output of Y-mills is certified by the ground truth of the corresponding task, and the loss is defined by the cross entropy. Due to the limitation of time, for more details about this scheme, please see the paper. And we go to the last part of this talk, is experiments. We adopted 3 public datasets to evaluate our methods. The details are illustrated in this table. Apparently, the datasets have different sample shapes and different settings. We're using all these datasets to test the 2-task version of Y-mills, but only CSIDA dataset and Y.3 dataset for the 3-task version. And there are several baseline models. The single task sensing model and the naive multitask sensing model. And the model adopting the homoscedastic uncertainty into naive multitask sensing model to address the task imbalance issue. Finally, and the multitask sensing model based on the knowledge distillation technique. Now, these 3 pictures shows the model structures of these models. The first is the single task learning model, the second is the naive multitask sensing model, and the third one is the structure of our proposed model Y-mills. By the way, it is worth to know that the uncertainty multitask sensing model and multitask sensing model based on the knowledge distillation have the same structures as the naive multitask sensing model, which is the middle one. This is the experiment result of 2-task sensing on ARIL dataset. We can see that the Y-mills has better performance than others, including the method ARIL that is proposed along with this dataset. And this is the result performance in the 2-task and the 3 tasks on Y.3 dataset. Compared with the other approaches, Y-mills has the highest accuracy in most tasks. And again, this is the result on CSI dataset. And this is what shows that the Y-mills is outperforms other models in most tasks. Okay, now this is another type of experiments. We try to use this to evaluate the task scalability of Y-mills. Specifically, we use the trained 2-task version model and add some modules to construct the 3-task version. And then we trained the added parts of the 3-task version and maintain the trained 2-task parts and to extend to the dual task. As shown in figure 5, the accuracies of these models, like the naive multitask sensing model or the multitask sensing model based on knowledge distillation, and the Y-mills increase steadily along with the growth of the training set ratio. Further, the accuracy of Y-mills always higher than the other 2 models. This shows that Y-mills has better task scalability than other models. And of course, the NERD common features is more general in Y-mills than that in other models. Okay, now let's move to the part like limitations and the future works. First, the Y-Muse only adopt the amplitude of a CSI. Even though there is some other researches have been pointed out that the phase of CSI contains useful information of the sensing tasks. However, the denoise methods for phase are specific to the format of the CSI sample. That means different data sets may need different pre-processing methods. Despite the Y-Muse has acceptable performance by only using the amplitude, it is necessary to exploit the phase data and adopt it in Y-Muse for better performance, and this is what we will do in future. The second is that the training scheme of Y-Muse is complicated. Since each task needs a pre-trained single task model as a teacher model, we need to simplify the scheme in the future work. And the next is that we only test Y-Muse on at most 3 tasks. We need to exploit more tasks in Wi-Fi sensing. And the last, the parameters of Y-Muse increases along with the number of tasks. This is an interesting point about how to use a statistic parameter model to handle different scale multitask sensing. Well, I've covered the points that I needed to present today, and now if you have any questions, I'll be happy to answer them for you.